Okay, at Hoover Dam, we convert gravitational potential energy into electric power. Are there any losses associated with that?
Well, I'm sure a lot of people died building the thing.
A lot of people died building the thing. Okay, so when he...
Ask for losses!
Yeah, I asked for losses, and, you know... I think you're right. I don't remember the number of people, but this was a Depression-era project. And anyone ever... What do you know about curing cement? It takes a long time, and it releases energy. Okay, as the cement cures, it releases energy. So if they wanted to just pour the dam and wait until the cement had cured, it would be about 1,000 years, and they were impatient. So how do you think they solved that problem? Yeah. He says they put pipes within the dam and ran water through them. Yeah, and they built the world's largest refrigerator to cool the water to run through the pipes, which of course are still embedded in the dam, in order to get it to cure on a reasonable time scale. So it's an amazing feat for the Depression. Yeah?
Doesn't concrete crack though if you don't cool it consistently and stuff like that?
She says, doesn't concrete crack if you don't cool it carefully or consistently? Yeah, so I'm going to assume empirically that they cooled it carefully. Good by you, Anya? Okay, so if we get 2 gigawatts of power out of the dam, what's the flow rate? What rate are they releasing water? So this figure, 180 meters of head, means they take water from the top or near the top of the reservoir, and they're releasing it down in the river below. You can kind of see a little bit of the river here, okay? And why is there this white region around the dam? Drought. Yeah, so it turns out that we're using the Colorado River in an unsustainable way, and the predictions are with global warming that it will never rise up to what it was before. So turn the water off when you're brushing your teeth. All right, so what is the rate at which water is flowing? Well, we have to worry about efficiency. Maybe you don't get all the energy out. Anybody have a guess for the efficiency of the turbine at, yeah? 89%. I was going to say 90, so I think that's a big, okay. Professor Durrett gets chocolate. All right. So 89%, that's pretty high. Okay, this is a straight conversion of mechanical energy to mechanical or electrical energy, and the conversion efficiency can be pretty good, okay, close to 1. So we might even just say it's 1 and ignore it. Okay, so what would be the flow rate of water? So the gravitational potential energy for a mass m would be mgh, and the rate at which the water is allowed to flow will give us the power. So m dot gh. So if we wanted to calculate the flow rate, I could divide the power by gh, and if I wanted to be more careful, I could throw in that 89% on the bottom, but I don't want to be careful. So 2 gigawatts over 10 meters per second squared, and 180 meters, which is a lot like 200 meters. I think it's almost indistinguishable from 200 meters. So 2 gigawatts divided by 2,000 is 10 to the 6 kilograms per second. Does that seem like a lot?
Well, given the size of that.
No? To me, that seems like an amazing flow rate. That's a lot of water. So I leave you the exercise. Imagine that we're draining, which is it? Is it Lake Powell is the one behind?
Lake Mead.
Lake Mead. We're draining it. What's the area of the lake?
A lot.
A lot. Okay, so let's say it's 100 square kilometers or something. Figure out how fast the water level is dropping, assuming that all the farmers have taken out all the water upstream, so there's no influx.